Okay, we're going to do a few more examples of finding slopes or other things with tangent lines to curves. And again, there may be more than one way that you know how to do this problem, but we're going to focus on doing this using the definition of the slope of a tangent line. Okay, so the first thing that you want to do is make sure that you know the definition. So I'm going to write that over here. The slope of a tangent line to a curve is limit as h approaches 0, f of c plus h. C is the point where you'd want the tangent line at, minus f of c all over h. All right, so that hopefully you know by now. If you've done very many of these problems, hopefully that's getting stuck in your memory. Okay, so let's see. When I look at this function and I try to do that, I'm going to say, all right, I'm going to do the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. All right, that would be for any function, finding the slope of the tangent line at the point x equals 0. And then, we're going to have a little trouble here. When I put 0 plus h into the original function in place of x, I'll just have 1 over h. But at the moment when I go and try to put 0 into that function in place of x, we should say no. We can't do that. I can't put 0 into that function in place of x because then I end up with 1 over 0, which is undefined. So what does that mean? It means that this function does not have a tangent line at that point. In fact, that function doesn't even have a point. Does not even have a point at x equals 0. So how could it possibly have a tangent line to the graph at x equals 0? And in fact, the reason we had a problem finding the slope of the tangent line using the definition here was exactly when we tried to write down what would have had to do with the point on that function at x equals 0. So this example is really intended to emphasize that not every function has a tangent line at every point on the graph, and we'll look some more at that later. Okay, let's look at another one though where we actually do have a tangent line to the function at a particular point. This is just a little bit more complicated function than we've worked with before. Okay, so we're going to find the slope of the tangent line. We're going to write down the definition with 3 in place of c. Okay, and so away we go. We're just doing this with this function. The algebra here is a little more complicated than some problems, but other than that, it is pretty much the same. Okay, so let's see. Inside these radicals, I have a little bit of simplifying I can do. I've got a plus and negative 5 that I can distribute through here. So inside that radical, I will have 4 plus 15 minus 5h. Okay, and then inside the second radical, I will have 4 plus 15, which is 19, all over h. So, all right, well, we did one a little bit ago, kind of like this in the previous video, where we had some messy radicals that we were trying to simplify. And hopefully you remember what we did then was we multiplied by the other factor in a difference of squares in order to rationalize the numerator. This works because we have square roots. If I had other kind of expressions here, we might not have things happen so nicely, but alright, so with this one though, when I multiply by that other factor in a difference of squares, we should be able to just keep going here. So square root of 19 minus 5h times itself, that will just be 19 minus 5h. And then I will have a plus square root of 19 times square root of 19 minus 5h, and a minus square root of 19 times square root of 19 minus 5h. Those middle terms will cancel. And then minus square root of 19 times square root of 19 will be just 19. Ooh, and so I get some nice cancellation on the numerator. Notice I'm writing LIM in front of every single step until I get to the end and evaluate that limit. Okay, so you might have noticed if you've done very many of these problems that there tends to be a lot of canceling in these problems. And so if you're doing these problems and not getting some canceling to happen, it could be that you've made some sort of mistake or you're just not seeing the canceling that you could be doing. Okay, so at this point I think we can go ahead and use a substitution shortcut. So I'm not going to write substitution shortcut theorem. So I'm not going to write LIM in front anymore because I am now evaluating this limit. So when I put in h equals 0, okay, my numerator doesn't come out too nice here. I end up with square root of 19 plus square root of 19, which is 2 times square root of 19. And okay, so there's a sort of ugly answer. That is an exact form answer. If you type it into your calculator and you get a decimal approximation, it is not the same. If you would like to rationalize the denominator just to make that a little tidier, you can. But unless you want your answer in a specific form, what I have in the box would be okay. Okay, so if I rationalize the denominator, I'll multiply by square root of 19 over square root of 19. And so then on the denominator, I would have 2 times 19. So that's negative 5 square root of 19 all over 38 is another form with the denominator rationalized. Okay, so we're going to look at one other sort of interpretation of what these things mean when we talk about this. So there's an important idea up here at the top and then an example problem that we will look at. Okay, so when we first started talking about secant and tangent lines, we talked about the slope of a secant line being the same thing as an average rate of change. Slope of a secant line is an average rate of change of a function on an interval. And so we haven't really talked a lot about sort of an interpretation in terms of rate of change about what slope of a tangent line would mean. But that's what's described here in red. We talk about that as an instantaneous rate of change. So something that's happening at a particular instant as opposed to over an interval. So you might notice here at a particular point, at a single point instead of being over a whole interval like we had for an average rate of change. Okay, so knowing which of these things we're being asked to find means that you're going to have to read carefully. All right, so this is kind of an example intended to help you understand why an instantaneous rate of change might make sense. The height of an object t seconds after it's launched is given by this equation. So this is an equation that would come from physics. Why this equation would be true, if you've had any physics, some of those coefficients in there may look familiar to you. But even if you haven't had physics, you can imagine an object being thrown in the air. It goes up and then it comes back down. And this gives the height as a function of time. Right? So we can think about, though, that height is changing instantaneously. So if I have like a radar gun on the object, I get an instantaneous rate of change of that object, telling how fast that object is going at any particular time. And so that's what we would be after when we talk about an instantaneous rate of change. Okay, so for the first part here, though, when I want to find the average rate of change, we're going to do that first. That's just slope between 2 points here. And this is worded a little bit differently than the problem statement up above. So instead of saying over an interval, a less than or equal to x less than or equal to b, it says over the first 2 seconds. But we have to interpret that to think about what that would mean. That would mean when time starts at 0 and goes to 2. So that's our interval. So for that average rate of change, we're going to just look at slope between those 2 points. So we'll have the function output at the second point at t equals 2 minus the function output at t equals 0 all over 2 minus 0. Change in output divided by change in input. Okay, so I think I'm going to go over here and make a little table of values of function input output values just to make my work a little bit easier. Okay, when I plug 0 into my original height function over here, those last two terms will go away, so I just end up with 10. When I plug in 2, let's see, I'll have 10 plus 50 times 2 minus 16 times 2 squared. So that'll be 10 plus 100 minus 64. So I think we'll get 46. So for the output when t equals 2. Okay, so our average rate of change will be the output when t equals 2, 46, minus the output when t equals 0, 10, all over 2 minus 0. Okay, so I'll just do the subtraction. I get 36 over 2, or 18. And that's a rate of change, so that would be in units of output. That's height in feet, feet per unit of input. And so these are second. All right, so and that's a positive rate of change. So we know that over those first 2 seconds, the height is increasing by an average of 18 feet per second. But if I'm watching the ball, I might actually be interested in what's happening at a particular instant for an instantaneous rate of change. All right, so that is an instantaneous rate of change. That is the slope of a tangent line. So we're going to need to use limit as h approaches 0 of, oh, we got a lot of h's here. I'm going to use f. I'm going to rename this function f of t since we got an h in our limit and an h in our function name. So f of 2 plus h minus f of 2 all over h. Okay, so I'm going to have to scroll up so that I have enough room to do this, but we're basically just going to do the same thing that we did before. Okay, so limit h approaches 0, put 2 plus h into the function in place of t. So 10 plus 50 times 2 plus h minus 16 times 2 plus h, the quantity squared, minus, all right, and then I need the function output when t equals 2. I think we have that over here from our table from before. So 46 all over h. Okay, and then we just need to do some algebra. I'm probably going to expect a lot of canceling to happen here. All right, so 10 plus 100 plus 50h, when I distribute that 50 through. And then on the next parentheses here, I need to be careful to kind of do this in the right order. So I need to do the exponent first. 2 plus h, the quantity squared, will be 4 plus 4h plus h squared. You got to FOIL that all out. And then I'll distribute the minus 16 through on that. Okay, so I need to be careful to make sure every little detail is correct here and I'm not losing a negative sign or forgetting a term. Okay, so I'm going to distribute through the minus 16. So I will have minus 64 minus 64h minus 16h squared, and then I still have my minus 46, and that whole thing is over h. Okay, so some like terms to combine here. Let's see. I got a bunch of constant terms, so let me just mark them off here. 10, 100, minus 64, and minus 46. Yeah, and those all add up to 0. Okay, so those all cancel. And then I have a couple of h terms. Those don't completely cancel, so it looks like I'm left with minus 14h and then minus 16h squared all over h. All right, so then I can factor an h out of the numerator. I have a common factor of h, minus 14 minus 16h left. And then another fun part, cancel. And okay, so now I can do a substitution shortcut for this limit. Limit as h approaches 0 of negative 14 minus 16h. Negative 14 minus 16 times 0, so I get negative 14. All right, and that is a rate of change of, again, units of output, feet per unit input, seconds, feet per second. All right, so the other important thing about this one is that that is negative. So what that means is that at t equals 2, our height is getting smaller. The height is going down. Height is going down by that much, by 14 feet per second at that instant. So the object is on its way back down at t equals 2, and although it's higher at t equals 2 than it was at t equals 1, it's on its way back down. So that would be an important thing to notice about that. All right, great.